Okay, so this will be about the quantum version of the log-rank conjecture. So let me remind you of the setting briefly. So there are two parties. They each have inputs x and y, which are n bits long. And they want to compute some Boolean function f of x, y of these inputs. So since none of the parties have the entire input, they have to communicate to compute this function. And we are interested in how much communication is needed to be able to compute this particular function. So let me define d of f to be the deterministic communication complexity of f with no error and no randomness. So in this setting, it's useful to view your function as a matrix where the xy entry is the value of the function on input xy. And I'll call this matrix A of f. And it's well known that if you have a communication protocol, the transcript of this protocol, or all the messages exchanged by this protocol, it gives you a partition of the matrix into rectangles. And in particular, if there were C bits communicated, then there are at most 2 to the C rectangles. If the protocol is correct, then these rectangles are also monochromatic, by which I mean that the function value is constant inside the rectangles, either all 0 or all 1. So what this implies is that you can write the matrix on the left as a sum of these 2 to the C at most rank 1 matrices. So the rank of the matrix on the left is at most 2 to the C. We're taking the log here. It shows you that the deterministic communication complexity is lower bounded by log of the rank. And the rank is always over the reals in this talk. Okay, so this is where the log-rank conjecture comes in. So log-rank is a lower bound on communication. But Lowas and Sachs in the late 80s asked whether it completely characterizes communication. So this algebraic measure of this matrix, it kind of tells you everything about communication. So the conjecture was that deterministic communication is bounded by polylog of the rank for any function f, Boolean function. Okay, so far the best bounds we have towards this conjecture are sort of exponentially far apart. The best upper bound is square root of the rank, and the best lower bound is log squared. So in this talk, we'll be concerned with the randomized and quantum version of this conjecture. So let me define R of epsilon and Q of epsilon to be the randomized and quantum communication, and epsilon is 0.01. That's throughout this talk. And in this case, it's known that another algebraic measure, which is log of approximate rank, is a lower bound on both of these quantities. And approximate rank is just the minimum rank of any matrix, that is epsilon close to your original matrix in each entry. And here it is an example, which will be also useful for us later, is the identity matrix of size 2 to the n. We know the rank is 2 to the n. But if you allow epsilon approximation, then the rank becomes n over polynomial in epsilon. So it decreases exponentially. And the reason for this is essentially hashing, or Johnson-Lindner-Strauss. Okay. So since another algebraic measure, very similar to rank, is a lower bound on both of these quantities, Lee and Schreibman asked whether both of these measures can also be upper bound by some polylog of these quantities. So they made these two conjectures that the randomized communication and the quantum communication is upper bounded by polylog of the rank, approximate rank. And one very interesting reason to study the randomized version was at least that it actually implied the log-rank conjecture. And up until recently, the best separations that were known for were polynomial. But probably most people know here that in a recent breakthrough last year, Chattopadhyay, Mande, and Sharif, they introduced a function where the log of the approximate rank is log n, but the randomized communication is square root of n. So this gives an exponential separation. And in this setting, we resolve the quantum version of this conjecture. So first, we prove a simpler, we give a lower bound, a square root n lower bound for a classical square root n lower bound on the same function using information theory. And once you have a purely information theoretic proof for the lower bound, you can generalize it using tools from quantum information. And we could prove that this function requires n to the 1 over 6th communication. And this disproves the quantum version of the log-rank conjecture. And there was, as the title slide suggested, that there was independent work proving the same by Anshu, Baudou, and Touchet using similar but slightly different techniques. And I will say a little bit about it at the end if I have some time. Okay, so that was the introduction. So for the rest of this talk, first I'll tell you what this function is and why its approximate rank is small. And then in the second part, I'll tell you how the quantum communication lower bound works. Okay, so the function is called the sinc function. It turns out that it was it's been around since the 70s in an unpublished work by Best, Manam de Boas, and Lenstra. Okay, but in another context, not in the context of communication complexity. So the function is defined on the edges of the complete graph with square root n vertices and n edges. So the parties have one bit for each edge. And a bit xe and ye, their parity, it assigns orientation to the edge e. Okay, which I mean that it's like let's take an example. So if the edge was uv, if the parity of the bits was 0, then the edge would be pointed one way. And if the parity was 1, then the edge would be pointed another way. Okay? So since you had a complete undirected graph, once you assign an orientation to every edge, it becomes a complete directed graph. And this function just asks whether there is a sinc in this graph. So if and only, so this function is 1 if and only if there is a vertex where all the edges are coming inwards. And one very important fact that will be useful for us later is that for every input xy, there can be at most one sinc in this graph. And the reason is because it's a complete graph. So if you have two vertices that are sinc, if you look at the edge between them, then that can only be pointed one way. And for the rest of this talk, let me introduce some additional notation. So let v be a vertex, and let n of v denote the edges incident on this vertex. And let me denote this so fixed orientation, which describes whether all the edges are coming inside by this variable z. Okay, so we fixed an ordering on the edges, so every vertex has a unique orientation, which makes it the sinc. So vertex v is sinc if and only if sort of the parity of this vertex is exactly equal to this fixed string, which tells you the orientation is the one that's coming inwards. Or more pictorially, if you view your entire input as n bits for all the edges, then all you're asking is that these particular square root n bits that are incident on this particular vertex, they are equal up to this fixed shift z. Okay, so this is when this function is 1. Okay, so now I can tell you the results a little bit more formally. So Chattopadhyay, Mande, and Sharif, they proved that the log of the approximate rank is log n in this case for this function. And in particular, removing the log, the rank is polynomial, approximate rank. And they also showed that the randomized communication is square root of n. And here we give a new proof of this work. The classical proof is actually much nicer than the quantum one, but I will not talk about it here. And the quantum communication of this function is at most 4th root of n, because you're looking for a sinc, so you can just do Grover search, and there are square root n vertices. But we proved that there is a polynomial lower bound here also. Okay, so let me tell you why the approximate rank of this function is small. The reason is very simple. So since we just saw that there can be at most one sinc in this any graph, you can write your matrix as a sum of indicator matrices where a particular vertex v is sinc. Okay, and this particular indicator matrix for a fixed vertex being sinc, this only happens when the two bit strings are equal on this square root n edges incident on that vertex. So this is essentially like a shifted identity matrix on a smaller subset of bits. And we just saw that this has small approximate rank. And you're only adding like square root n of them. So you can get a very good approximation for this matrix that is still small rank. So that's essentially the basic idea. Okay, so that finishes this part. So let me move on to the quantum communication lower bound now. So again, if you're not familiar with quantum, you can just replace everything with randomness, and because the proof strategy, high-level ideas are the same. So let me briefly remind you the setting. So we have a 1-qubit channel. And we also give the players access to some initial entangled state, theta AB, where AB are their work registers. And the input is given to the parties in this mixed state with amplitudes given by the input distribution. And the output of the protocol is obtained by measuring the final qubit of the channel. Okay, so we're going to show a lower bound on n to the 1/6 on this function. So the basic idea is as follows. So consider a fixed quantum protocol, and let's feed it different input distributions and look at what the behavior of the protocol is. So if we feed this protocol the distribution on the left, which is uniform distribution conditioned on having no sink, so the output of the function in this case is always 0 because there is never a sink. So I'm calling this distribution P0 and the state O of C. And on the right, you have a distribution where a fixed vertex V is sink. So in the end, we will pick this vertex at random. But the main point is in this distribution, there is always a sink. So the function is always 1. So if your protocol had low error, it should be able to distinguish these two distributions. Just the final bit of the protocol, the final qubit, measuring it should give you very different answers, 0 in one case and 1 in another case. But actually, we're going to show that if the protocol had small communication, then these two states, marginal states on the channel, they are actually going to be pretty close. And to do this, actually, we go through an intermediate distribution. So we feed the protocol the uniform distribution. And we show that the state it generates is close to the states on the left and the right. Okay. So essentially, the states on the left and the right are more or less, measuring them produces a uniform random bit if the communication was small. So this is like the high-level plan of the proof. And if you do some thinking, a little bit of thinking, it turns out that it's not very hard to see that under the uniform distribution, there is almost always never a sink. So with probability like 2 to the minus square root n, there is a sink. So the distribution on the left is obtained by conditioning on this event of probability almost 1. So even the input distributions are close in this case. So the outputs are still going to be close. So this part is easy. So the interesting part is to prove that the distribution on the middle and the right, they generate close messages. The final states are close, even though the input distributions are very far apart. And in particular, we're going to prove that the states are going to be epsilon cubed close if the communication is smaller than that quantity. Okay. All right. So one helpful fact to keep in mind is how are these two distributions related. So this event V sync is actually, as we just saw before, that is equivalent to this event that these particular subsets of bits are equal up to this fixed shift. So essentially, I will call this event like a collision event because you're requiring that these two subsets of bits they collide. So to prove this claim, our plan will be as follows. So if we pick a vertex V at random, only 1 over square root n fraction of all the n edges are incident on this vertex. And to know whether this vertex is sync or not, you need to look at all those edges, the inputs for all those edges. So we're going to show that if the parties don't know where this vertex is, then they communicate a lot of useless information. And the parties, they learn very little information about these relevant inputs under the uniform distribution. And then we show that conditioning on this collision event has small effect to go back to our input distribution. Okay, so this is the plan. And the first part, so let's say the parties communicate this L qubits, where L is the same quantity as in the claim. And one can show that in this setting that the amount of information the parties learn about the other party's input is at most 2 times the number of qubits communicated. Okay, and here we have a very crude way of measuring information, just like the party that has access to Y, B, and C, how much information does it learn about X, which is held by the other party. So overall, they learn 2L bits about all the edges in the graph. And we're asking, if you look at a 1 over square root n fraction of them, how much information do we learn? So ideally, we would like to say that if you look at a 1 over square root n fraction, we learn 1 over square root n fraction of the total information. And essentially, this is this is implied by Scherer's inequality, which I'm not going to talk about, but it should be pretty intuitive for most people here. Okay, so this is straightforward. So the next part is this conditioning on this collision event. And here also, luckily for us, we can just use something as a black box. There was a lemma proved by Anshu Tushat and Yu, which is a quantum generalization of a previous lemma of mine with Anuprao, which exactly captures this setting. So suppose you have an L-qubit quantum protocol, and you feed it two different distributions, uniform distribution and a uniform distribution condition on this collision event, and look at the states generated. Then these two states are actually pretty close to each other, where the error is given by the square root of the mutual information after each step. Okay? So essentially, if the mutual information is small, then these two states are more or less independent, and the final error is also small. And the crucial point is that here the distances add up after every round. So in the classical case, this does not happen. That's why you get like much better bound. Okay, so once you have this, we just saw that the amount of relevant information the parties learn is roughly L over square root n, where L is the communication. And if you plug it in this lemma, just work out the calculation, everything is set up so that you can, the final error is at most epsilon cubed. Okay. All right, so just to recap, to analyze our protocol, we fed it different distributions. On the distribution on the left and the right, the outputs are different, so the protocol must be, the states must be far apart if it was good. But if we just showed that if the protocol had small communication, then these two states are actually pretty close by going through an intermediate distribution. And the same idea also works in the classical setting, but the analysis is more clean. Okay. All right, so let me just briefly mention a few words about the approach of Anshu, Boudou, and Touchet. So what they give is a sort of direct sum reduction. So they say that if there is a C-qubit protocol for this function, then using just the same Scherer's inequality that we use, there is a C square over square root n protocol for equality under uniform distribution, but now you're measuring like the information cost of this protocol, which is again like the same quantity we used. And then they proved that the information cost must be at least 1 over C, using some cut and paste arguments. So essentially their high level abstraction is different, but I think the proofs are pretty much doing the same thing under the hood. And both this argument as well as ours also give you round dependent lower bounds here. Okay, so that's essentially it. Let me conclude with the open question. What's the status of the log rank conjecture? So this function doesn't tell you anything about it because it's essentially equality or identity. And identity has large rank, but also has a large communication. So it doesn't shed any light on this. And in particular, this conjecture, which might be more easier to think about, is can you bound the randomized communication complexity of a function in terms of the polylog of the exact rank of the matrix? So this is a nice question, and in fact, this is equivalent to the log rank conjecture by reduction of Gavinsky and Lovett. So I guess that's all I had. Thank you. No, you can prove square root approximate rank times log of rank, but like I don't think it works. Yeah, I mean probably one of the reasons why this sort of breaks, this counterexample exists in some sense.